Okay everybody, so in this video we're going to be talking about the reactivity of carboxylic acid derivatives with aldehydes and ketones also included for comparison. Alright, so one main point that you should keep in mind is that carboxylic acid derivatives can undergo a type of reaction known as a nucleophilic acyl substitution reaction. Okay, and for one particular carboxylic acid derivative, it's easier for it to undergo this type of reaction compared to another carboxylic acid derivative. Okay, and we're going to look into that in a little bit, right? But before we get to that, just keep in mind that an acyl group, like right here, nucleophilic acyl substitution reaction, an acyl group is basically just this, RC double bond O. Okay, so the mechanism of this reaction is as follows. You have your RC double bond O, your leading group, right here, okay? And you have an electrophilic or partially positive carbonyl carbon, and you have your more partially negative carbonyl oxygen, okay? And let's say we have a negatively charged nucleophile that wants to attack here at the electrophilic carbonyl carbon. So as a result, some electron density gets pushed up. You have something called a tetrahedral intermediate, but then the leaving group is good at leaving, so it gets kicked off, and then some of the electron density gets pushed over here. So you basically reform your C double bond O carbonyl bond, okay? And as a result, the main point of this, the main effect, is that the nucleophile replaces the leaving group, all right? And another thing you should keep in mind is that aldehydes and ketones don't like to undergo this because they don't have good leaving groups. An alkyl group, in the case of a ketone, is not a good leaving group, and in the case of an aldehyde, hydrogen is also not a good leaving group. So as a result, aldehydes and ketones would rather undergo a nucleophilic addition reaction, and this is the mechanism for an addition reaction under acidic conditions. So we have here a ketone, okay? And it gets protonated by this H plus just floating around because we are in acidic conditions after all. It gets protonated, a neutral nucleophile attacks, but the nucleophile has a hydrogen attached to it. You have a tetrahedral intermediate, but here we have a base that protonates the H. The electron density from the sigma bond gets kicked over to the nucleophile, so the nucleophile remains neutral, and you have this as your final structure, okay? So those are just the mechanisms, and before we get to the reactivity scale or the order of reactivity for carboxylic acid derivatives and aldehydes and ketones, just keep in mind that the order of reactivity is influenced by three main factors. Number one, resonance and resonance stabilization. Number two, electronegativity and the power of electron withdrawing groups. And finally, steric hindrance, excluded volume effects, etc. Okay, so here we have the scale. So basically speaking, okay, here we go. So acid chlorides are the most reactive, okay? So acid chlorides want to undergo nucleophilic acyl substitution reactions the most out of all the carboxylic acid derivatives, okay? So the acid chloride is the most reactive, followed by the acid anhydride, followed by the aldehyde, followed by the ketone, followed by the ester, which has a similar reactivity to a functional group called the imide, okay? But the least reactive out of all of these is known as the amide, alright? So why is this? Well, first we're going to be comparing the ester versus the amide. Why is the ester more reactive than an amide, okay? So we can analyze this using resonance stabilization. Here we have a valid resonance structure for the ester. Here we have a valid resonance structure for the amide, okay? And keep in mind that nitrogen is less electronegative than oxygen. So as a result, nitrogen is more willing to donate electron density to the carbonyl carbon as shown. So as a result, let's say we have a nucleophile that wants to attack the carbonyl carbon here. Well, this carbonyl carbon is the carbonyl carbon as a result, the carbonyl carbon for the amide is less electrophilic. It's less partially positive than the carbonyl carbon for the ester, right? Because this is a happy situation. Because after all, nitrogen is less electronegative than oxygen. So if you take away some electron density from nitrogen, it's not really going to care that much. And it's like, okay, fine, I can give some of my electron density to the carbonyl carbon. I don't care that much. But for the ester, this oxygen over here doesn't really want that positive charge. So it's going to want this electron density back. So as a result, this carbonyl carbon is actually going to be more electrophilic and more partially positive than this carbonyl carbon of the amide, my bad, okay? So that's why the ester is more reactive than the amide. Alright, and the second main comparison that we can make is the aldehyde versus the ketone. So this is mainly analyzed using steric hindrance. Alright, so here we have a teeny weeny hydrogen in the case of the aldehyde, and for the ketone we have this monstrosity. So when you have a nucleophile that wants to attack over here, you have a teeny weeny hydrogen in the way, and there's less steric hindrance, there's not as much in the way compared to this one, because if the nucleophile wants to attack over here, it's going to have this big monstrosity over here, and who knows what this could be, right? So as a result, a nucleophilic addition reaction is going to be easier for the aldehyde compared to the ketone because there's less in the way. If in the case of the aldehyde, it only has a teeny weeny hydrogen. Okay. So we can continue to analyze why the reactivity scale is in this order using the power of electron withdrawing groups. Okay. So we have to look at the degree of strengths of electron withdrawing groups, which have the abbreviation of EWG, okay? So let's look at the acid chloride, the most reactive of the carboxylic acid derivatives. This chlorine is very, very electronegative. It just pulls electron density away from the carbonyl carbon. So this carbonyl carbon right here, it is really partially positive. It is really electrophilic. So as a result, if a nucleophile wants to attack, it sees, hey, this carbonyl carbon, it's missing a lot of electron density. So I can easily, boop, just attack because after all, chlorine helped me. Chlorine helped me take away a lot of the electron density, so my job is easier and the reaction is more likely to occur, okay? So as a result, the reactivity increases in the case of the acid chloride, all right? And the chloride is the electron withdrawing group. This can be seen as the EWG, the electron withdrawing group. Now, in the case of the acid anhydride, it has two electron withdrawing groups. If you're looking at this carbonyl carbon, all this is the electron withdrawing group, right? This wants to take electron density away from this carbonyl carbon. But if you look at this carbonyl carbon, all this is the electron withdrawing group. All this wants to take electrons away from this carbonyl carbon. So you might be thinking, oh, wait a minute. I have two electron withdrawing groups, but this acid chloride, this puny acid chloride only has one. So why isn't the acid anhydride more reactive? And the answer is resonance, because this oxygen atom could push its electrons over here, or it pushes its electrons over here. If it pushes its electrons over here, for example, these electrons could get pushed up here, and you would have a valid resonance structure. And if it pushes its electrons the other way, the opposite effect would take place. So because you have resonance stabilization, the reactivity for the acid anhydride is weakened. Okay? And next let's go to the ester. All right. So for this carbonyl carbon, all this is the electron withdrawing group. The oxygen, it wants to take away the electron density from this partially positive electrophilic carbonyl carbon. However, let's compare the acid anhydride and the ester. Both of them are resonance stabilized, right? But the acid anhydride has two electron withdrawing groups, while the ester has only one. So as a result, the acid anhydride kind of wins out, and the nucleophilic substitution reaction, known as the nucleophilic acyl substitution reaction, is easier to do with the acid anhydride compared to the ester because the acid anhydride has two electron withdrawing groups and the ester has only one. Okay? And next, let's go to the amide. It also has only one electron withdrawing group, just this, but remember that nitrogen is less electronegative than oxygen, okay? So as a result, the power of the electron withdrawing group is less because nitrogen is less electronegative, so this electron withdrawing group isn't as strong as the electron withdrawing group here, okay? And finally, we can look at the imide, okay? Why do esters and imides have a similar reactivity, okay? And the answer to this is that the imide has two electron withdrawing groups, right? However, it has the less electronegative nitrogen atom. But when you compare it to the ester only has one electron withdrawing group, but the ester has the more electronegative atom of oxygen. So these effects kind of balance out, and as a result, you have similar reactivities for both of these carboxylic acid derivatives, okay? So this is a brief overview of the reactivity scale and the order of reactivity for carboxylic acid derivatives. I hope this video helped, and thank you for watching.